Here's I found this question in 13.6. There's a question here, number, well, there's a number, number 33 might be kind of interesting. Number 33 it's this kind of a function. F of x, y, z equals, and it is the square root of x squared plus y squared plus z squared. The square root of x squared plus y squared plus z squared. They also tell me I'm at the point, I'm on a point 1, 4, 2. So I'm at the point 1, 4, 2. You know, this is, of course, maybe you can read quickly and that you've got yourself a four-dimensional function here. You no good way to draw a picture of this guy at all. He's a four-dimensional function. But the concepts that we're learning in this chapter apply to functions of several variables. For what is the question? The question on this is find the gradient of the function and the maximum value of the directional derivative at the given point. Okay, well, they want the gradient. You know, I mean, this is funny, but this is a four-dimensional function. It's hard for me to talk about this, but his gradient would be this vector, fx, fy, fz. I mean, that's what it is. But this is not quite, I wouldn't really necessarily and this vector points in the direction of maximum slope, except I'm on this four-dimensional function. I don't even feel like I should use the word slope, but this vector points in the direction of greatest increase in W. You know, you could say that. In order to do this partial derivative, these partial derivatives, I mean, that's part of this exercise. You just need to do these partial derivatives. I don't think they're too hard. Well, let's do one here. Let's do this guy right here. A little fx. If I wanted to do fx, how would you do it? I think you would bring the 1/2 down, don't you think? 1/2, all this stuff to the negative 1/2. Right? 1/2, all this stuff to the negative 1/2. X squared, when I say all this stuff, I mean x squared plus y squared plus z squared. Times the chain rule, though. What's the chain rule going to spit out here at the end? A 2x, he's right. Right? The derivative with respect to x would spit out a 2x. And then this derivative's over. Here, if I clean up this derivative, it is the 2's cancel, and I could rewrite this as x over that square root. So to tell you the truth, you guys, after just that one example, can you do this with respect to y? Well, there's a lot of symmetry in these derivatives sometimes. If you do this with respect to y, don't you think it's the same thing? Yeah, if you follow the pattern, right. So anyway, yeah, there it is. And for z, same kind of thing. So some of these functions have a lot of symmetry to their derivatives when you work with them. But then at this point, 1, 4, 2, I guess I could plug this in. I mean, here it is in general. This is the gradient in general. If I do this at the point, then maybe I should have a little x, y, z here to indicate this is the gradient at any point, x, y, z. Now I'm plugging in the point 1, 4, 2, and I'll get a vector here. If you plug in a 1, 4, 2, I wonder what this denominator is if you plug in a 1, 4, 2. 4, 2. Square root of 21? 1, 4, 2. Square root of 21. So I guess I get this vector. 1 over the square root of 21. When you plug in y, you get 4 over the square root of 21. When you plug in z, you get 2 over the square root of 21. Okay. This is funny. This is a 3D gradient, but it's not exactly that 3D gradient I discussed in yesterday's class. But it's a 3D gradient. It points me on this four-dimensional function. This is a four-dimensional function. It points in the direction of greatest increase in the function. The gradient is a vector that points in the direction of the greatest slope or the greatest rate of change. It points in the direction. What is that actual greatest rate of change? What is that actual maximum slope? The magnitude of the gradient. And they did ask for that. They asked for find the maximum value of the directional derivative. So that is the maximum slope or the maximum derivative. And that would be the magnitude of this guy. Hey, at this point, we could do the magnitude of this guy. Let's do the magnitude of this guy. It'd be the square root of him squared plus him squared plus him squared. That's pretty easy, I think. What is that? Him squared plus him squared plus him squared. Hang on. That's 1 over 21, him squared. 16 over 21. 4 over 21.
21.
That's 21 over 21?
It's just 1.
That's just 1.
21.
That's interesting. His magnitude is 1. Hey, what would be his magnitude if I did it at this point? What would be his magnitude if I did it in general? Here I go. In general, I want to do his magnitude. Okay. Well, it's him squared plus him squared plus him squared in a square root. You're right. Him squared would be x squared over this, y squared over this, well, this denominator squared, and then z squared over this denominator squared. So then they all have a common denominator. So when you add it up, your numerator will be x squared plus y squared plus z squared over the common denominator, which is x squared plus y squared plus z squared. So it wasn't that it was equaled 1 only at this point. Actually, it equaled 1 in general. That's interesting little gradient. This gradient always has a magnitude of 1. Oh, oops. His magnitude is 1. Sorry about that. His magnitude is always 1. Wow. Well, anyway, that was fun. I'm not sure what the ramifications are. I'm searching for some. I don't really see any. I just picked a problem. It was fun how those variables worked out, though. You know, I don't know. I don't want to confuse you, but maybe I did. I sort of just confused myself, to tell you the truth. I'm working on a 3D gradient in a 4-dimensional function. I'm having trouble. I'm trying to visualize. I can't draw this. I can't do anything. And it's not my big old 3D gradient that I was talking about yesterday. You know, the 3D gradient I was talking about yesterday was this with capital F. And that 3D gradient is when you have a surface. That 3D gradient is normal to the surface. It's normal to the surface. And then so it served as a good normal vector for my tangent plane, is what it did in 13.7. But how come that's not this? Let's see. See, what is big F? Is big F a 4-dimensional function? This is a 4-dimensional function. This is x, y's, and z's equal w. Is that what big F is? No, big F is just x, y's, and z's equaling 0. So it's still just 3D. It's sort of a trick, though. Yeah, you're right. So big F is just, is when you have, it doesn't equal W, it's just all your X, Y's, and Z's are all on one side equal to 0. So if I called this 0, then I could call this big F, and then he is some kind of surface. I don't know what he is. No.
Point.
I know, he's weird. Anyway, maybe I don't want to do this. I'm taking problem 33 and I'm adapting it to something else, and maybe I don't want to do that. Well, I don't know. Now I got to. All right, hang on. I said maybe I don't want to. So if we did make this equal 0, then now we got some three-dimensional surface. I can maybe sketch him or think about him. Well, I think one thing I would do is square both sides, and then I'd have this. Oh yeah, that does.
What?
I said that was a point.
Yeah, you said point. You know, it does make me think. It does. You guys, somebody said sphere, but it's not a sphere unless you want to say it's a sphere of radius 0, which coincides with called it a point. A sphere of radius 0 sort of is a point. Is that all this is a point?
If you move the x squared and the y squared over and factored out the negative, wouldn't that be an upside down elliptical cone?
Okay, so that's a good point. He says move the x squared, y squared over. They're both negative, but this is bad. See, now I have a z squared equaling a negative number. How can z be squared and equal a negative number? I mean, see, this is producing this is nothing. See, what would the cone be? The cone, here's the cone. This is the cone. And then when you take the square root, the plus and minus version of this square root would be the top or the bottom part of the cone. So this that we had up here a second ago,
it's not the same thing.
It's not that, and so it's and you're right. I think you're right. I think it's a sphere of radius 0. I think it's a point. Okay, well, a point ain't much of a surface.
Isn't everything normal to that?
I mean, everything.
Everything, every line coming out of that is going to be normal.
Okay. I'm going to stop. Yeah, I'm going to stop. Now, I can think of another good question, or I can find another good question, or I can stumble into some weird stuff. But do you guys have any questions? Anybody wander in here with a good question? All right, well, I found that in 13.6. I kind of regret it. What else can I find in 13.6? I asked you to do 49. I did something similar here. Let me try this 48, although it looks kind of easy. I'm in 13.6. 48 is f of x, y is this, x squared plus y squared. And they give me a c value. They give me a c value of 25, and they give me a point 3,4. So they're saying c is 25, and they're saying I'm at this point 3,4, point called p 3,4. And then I should read the directions. The directions say this. Find a normal vector to the level curve at this point. So when someone says find a normal vector to the level curve, I mean, we learned just the other day, we learned something important. Thank you. The gradient is normal to the level curves. And so it's funny, they didn't say find the gradient, but they said find a normal vector to the level curves. Well, that means find the gradient at this point.
What is this equals?
So how do you find a gradient? Now we're back to 2D instead of this weird, this was a 4D function with a 3D gradient. This is a 3D function. It has a 2D gradient. It is, fx, fy. It points in the direction of maximum slope. In general, it would be pretty easy. What is it?
2x, 2y.
2x, 2y. Oops. At this point, I can plug it in and get an answer. At this point, the gradient at the point 3, 4 is 6, 8, I guess. So I've answered their question. I'm done. I'm finished. I think I would add this to the question if I had this on my test or quiz or take-home quiz. I would say, please illustrate everything you've just done. So here's what that means. First of all, you don't really have to draw the function, but while we're on this topic, do you know what that function looks like? It's a 3D thing. Do you know what it is? You was just speculating about cones a few minutes ago. He's not a cone. What is he? He's famous.
He's a spherical paraboloid?
Yeah, spherical's not the word.
Just elliptical.
Yeah, paraboloid. But he's a paraboloid sitting here. That's good. You said elliptical paraboloid. Again, this one happens to be circular.
Yeah.
Nice circular paraboloid. That's what he is. Anyway, when C is 25, that I will be looking at the level curve when C is 25 or when Z is 25. That's what those C values or Z values. I could plug it in and I would be looking at this level curve. That's way up there somewhere, or I'll mark that 25. That would be this level curve right here, you guys. And if I looked at it just in the XY plane, it would be here. It would be a circle of radius 5. Right, you guys?
Yep.
And I think if you're a circle of radius 5, I think this point 3, 4 is on that level curve. This point 3, 4 is on that level curve. If you go over 3 and up 4, over 3 and up 4, there you are. You're on that level curve. So I got a level curve labeled C equals 25. It came from that 3D picture. It's a 2D level curve. At that point, on that level curve, I should be able to draw this gradient vector. And it will look like it's normal to the level curve. It should. 6, 8. That would mean go over 6. That's a 3 and a 4. That means go over 6 and go up 8. I'll be darned. Looks totally perpendicular, doesn't it? So there's a picture of your little 2D gradient. It must be pointing to the, it's pointing out there. It's pointing out. It's not pointing in. Let's look up here at this picture. You're up here. You're at this point 3, 4, and that vector is pointing out here, right? It's pointing out. I mean, here's this picture put up there. But if you're on the edge of this paraboloid, where would you head for maximum slope? Would you head back toward the interior of it? I guess not. That looks like if you head toward the interior, you're falling, right? If you point yourself toward the interior of this paraboloid, and the slope is negative. It's falling toward that minimum, toward that valley. So the direction of maximum slope is where it's rising in front of me, which is out this way. On the edge of a paraboloid, that way is the direction of maximum slope. It's steep. Huh. You guys all right?
Mm-hmm.
Yes?
For this question, since they didn't want the level curve or how to draw it,
Yeah.
They just kind of threw that c equals 25 to throw us off.
Yeah, I wouldn't say throw it off. No, that wouldn't. Nobody does that. No, I wouldn't characterize it like that. But you didn't seem to use it, did you? So it was just, yeah, it's there. It's just there to kind of complete the question of.
C equals 25 when you're at that.
I mean, that's the level curve.
Yeah.
Yeah, that they wanted you to
But we would have used
find a gradient, find a normal vector to the level, to that level curve at that point. And you're right, if they're going to give me a point, they did or didn't have to tell me which level curve it was on.
unless they wanted you to sketch.
Right,
Yeah.
right. Well, even if I did, even if they didn't tell you that, you could sketch it. If you are at the point 3, 4, you could plug it in and find the z value, couldn't you?
Yep, 9 plus 6.
When x is 3 and y is 4, you could find out that z is 25, and then you could talk yourself into saying, oh, okay, then that's the level curve I want to look for.
Yep.
When z is 25, I'll let c be 25, and right. Okay. 13.7 was about these tangent planes, which brought up this other kind of gradient, this capital F gradient that we started to talk about. It's really just used in 13.7 for tangent planes and normal lines. I kind of like these questions. Let's. Okay, I don't even think I assigned this, but I like this. You ready? Okay, I'm up in 13.7. I like this 61 and 62. They're good questions. I think I'll try 62 and let you try. So I'm up in 13.7 and I want to try this 62. And it's kind of a proofy little problem. It's a funny little problem. 62 says, show that the tangent plane to the quadric surface at the given point can be written in this form. Actually, they're not at the point x naught, y naught, z naught. So they're doing everything very abstract here, you guys. They're giving me a hyperboloid. They called it a hyperboloid. I don't care if you know that. And it is x squared over a squared plus, y squared over b squared minus z squared over c squared equals 1. That's just a general, generic, funny hyperboloid, huh? Yep, that's what it is. Here's what they say. They say that the tangent plane, is going to be this. They say the tangent plane is going to be this. X naught over a squared, yeah. X naught x over a squared. Y naught y over b squared. Z naught z over c squared equals 1. Wow. That's going to be the tangent plane. This is very abstract and strange looking. We're going to find the tangent plane, so that, and that's supposed to be the result over there. So we're kind of proving this. Find the tangent plane at x naught, y naught, z naught. Are you guys okay? Mm-hmm. Just, you got some generic surface. It's not that generic. It's a hyperboloid, but the a squareds and b squareds and c squareds are constants. We're at some point here in general, x naught, y naught, z naught. Now, if I want to go through the procedure of finding the equation of the tangent plane, I think I need big F. Now, how do I get big F? And then I'm going to take the derivatives and get the big F gradient. But first of all, I need big F. How do you turn this into big F?
Make it equal to 0?
Yeah. to call him big F, he needs to be all the x's and y's and z's on one side equal to 0. How do you do that? Move the 1 over, right? I mean, that's how you call it big F. Now, I don't even feel like doing that, but I'll do it. X squared over a squared plus y squared over b squared plus, minus z squared over c squared minus 1 equals 0. But when it equals 0, that's what I call big F. That's how you rename it big F. And now what I want is, I want big F partial derivative with respect to x. And that is not difficult at all. And to tell you the truth, I could have got it without moving the 1 over, right? I mean, the big Fx here is the same as big Fx here. And that's going to be true for big Fy and big Fz. But technically, moving the 1 over, let me call it big F. Now, big Fx is the partial derivative with respect to x. The a squareds, b squareds, and c squareds are all constants. We're going to treat the y's and z's like constants, apparently. What is this derivative?
2x over a squared.
2x over a squared. Cool. What's big Fy? Again, there's a lot of patterns when you start doing these problems sometimes.
2y over b squared.
2y over b squared. What's big Fz?
Negative 2z over c squared.
Negative 2z over c squared. Hey, when I wrote this, did I write this right? No, I screwed up. When I said we're trying to prove this answer has a minus sign in it. Sorry, this answer had a minus sign in it. All right, so now what do I do? This is my, if I wrote this as a gradient, I mean, but here it is in general. I've got this at any x, any y, any z. What point do you want to evaluate it at?
X naught, y naught, z naught.
X naught, y naught, z naught. That might not feel too specific to you, but it's more specific than x and y and z. I mean, you plug in this point for x naught, y naught, and z naught, and then it's, and so at the point x naught, y naught, z naught, we're plugging that in, and we get, more specifically, 2x naught over a squared, 2y naught over b squared, and negative 2z naught over c squared. See, now these are numbers. Are you guys okay with that? There's no variables in there.
No.
Now it's a number. And this is what I'm calling my 3D gradient. It is the normal vector to my tangent plane, and it is a vector, and I'm going to write it 2x naught over a squared, 2y naught over b squared, 2z naught over c squared. Negative on that last one. I keep losing that negative on that last one. Thank you. So now what do I want to do? I got my normal vector. Hey, I got my normal vector, I got my point, and when you got a normal vector and a point, can you write the equation of a plane?
Yep.
This is from chapter 11, you got to remember it, but we would write the equation of the tangent plane would be my normal vector times x minus x naught, right? Plus my normal vector, y component of my normal vector, times y minus y naught. And then my normal vector z component times z minus z naught, and it equals 0. That's your tangent plane. Now, I got a little more work to do to prove. I'm trying to prove that it's that, right? I'm trying to show this is what they wanted. Show that this is the answer. So I'm right here. I haven't quite showed them this yet. You know, I'm going to do a couple moves. I think I will distribute these. Is that okay with you?
Yeah.
But before I distribute, I got a bunch of extra 2's I don't really care for. You know, I can divide by 2 at any moment. You know, I can divide by 2, and it's gone. Divide by 2, it's gone. Divide by 2, it's gone. And what about over here? Divide by 2, and it's still 0. So I can just knock out that 2, dividing by 2. But then I'm going to do that, and then I'm going to distribute this. So I'm going to have x naught x over a squared minus x naught squared over a squared. Is that? Wait a minute.
Yeah.
I'm getting confused.
Yeah.
I cancel the 2, and then I distribute x naught x times over a squared, x naught squared over a squared. Okay. I cancel the 2. Y not y? Because. Y not y over b squared minus y naught squared over b squared. Yeah, that's right. Huh. Then this is a negative, oh, I canceled the 2. Negative z naught z over c squared, and then when I distribute, it'll be a positive z naught squared over c squared. Huh. Equals 0. See, I'm trying to get that answer. This is kind of strange looking. Let's see, what if I move all these guys over to the other side, and not all these guys. These constants, right? So now I do have a variable x. This is my plane. I got a coefficient in front of x. I got a coefficient in front of y, and a coefficient in front of z. Those other terms are numbers. There's a number, there's a number, there's a number. If I throw them all over to the other side, I don't know, according to this, it should be a 1. I don't know about it. Let me see. X naught x over a squared. Okay, I'm leaving this y naught y over b squared. I'm leaving this here. I'm going to have a negative z naught z over c squared equals, and then on the other side, I'm going to put that x naught squared over a squared, that y naught squared over b squared, and that negative z naught squared over c squared. What the hell is going on? This is getting confusing. You know what, though? I've got my left-hand side equaling my left-hand side. But to prove that this is this, I mean, I need all that to be a 1.
Use that property.
Well, we are on a hyperboloid. And if you plugged this point into the hyperboloid, you would plug x naught in and y naught in and z naught in, and guess what you would have? X naught squared over a squared, y naught squared over b squared, minus z naught squared over c squared does equal a 1. When you plug this point into the surface, it's a true fact that that crap equals 1. And that's what that is, right? That point plugged into the surface is right here, and that is 1. So we proved it. That's kind of a fun little problem. We found the equation of a tangent plane, kind of in general, but not only did we do that, we did a little cleaning up here at the end. I like that problem. That was 62. There's a 61 if you wanted to practice it, but it works real similarly. Okay. This is confusing. It says quiz Friday, test Friday. Next Friday? Okay. Well, I don't know, man. I could ease on into 13.8 here. Unless you guys got any questions you want to slow me down, slow down the train. You could pull the emergency brake, you know, maybe slow down the train. You're not interested. You like fast trains. I got you. All right. All right, let's keep the train rolling then. 13.8 is fun. Listen, we're getting toward the end of this chapter. And what we do now is we teach you how to, we're going to find mins and maxes in 3D. Mins and maxes in 3D. We've already previewed this a little bit. We said, you know, we're probably going to have a min or a max when we get both partial derivatives to be 0. If you get both partial derivatives to be 0, then if you're standing on a point and both partial derivatives are 0, then that means the duff is 0 in any direction. So that means the slope is 0 in any direction. You're standing on the top of a hill, or at the bottom of a bowl, or at a saddle point. You're standing at a place where the slope is 0. That might be a min, it might be a max, or it could be a saddle point. In 3D, there's a saddle point is neither a min or a max. A saddle point it's tough for me to draw. The book has some good pictures, but it kind of comes from that saddle. You know, when you're sitting up, a saddle. When I'm sitting on a horse, riding a horse, right where my butt sits, right on the saddle there, is a saddle point. You know, from one direction, like when you look this way at the horse, and by the way, it's a very sway back horse, you know what I'm saying?
Oh. Dang. That's nice.
Thank you.
Oh.
That's his tail. But you know, a horse. Anyway, when you're sitting there on that saddle, when you look at it this way, it looks like I might be at a min. But if you look at it this way and get his butt and neck out of the way, then it looks like you might be sitting at a max. Okay, but it's not. It's neither a min or a max. It's a special point. It's a saddle point. It's a place where it's a level place. It's a place where the slope is 0 at that place. The slope is 0 at that place, but it's not a min or a max. It's a saddle point. But where do those happen? I mean, to start classifying mins and maxes and saddle points, though, the first thing we need to find is critical points. We call them critical points. And critical points, my little bit of this is defined in the book, but I'm going to say a point, x naught, y naught, is a critical point of some function f of x, y, you know, z equals f of x, y, if, number 1, f partial derivative with respect to x at that point, we've already said this, now I'm writing it, that the partial derivative with respect to x is 0, and the key word is and there, the partial derivative with respect to y is 0. So it's this concept, we've said this before, that this derivative is 0 and this derivative is 0. When they're both 0, then you're at a critical point that could be a min or a max. But it's funny, it's and. So you're kind of solving two equations. You want to know when this is 0 and at the same time, when is this 0? I mean, right? You might find some points where this is 0. And you might find some points where this is 0. But the only ones that are really critical points are the ones that make it both 0. Or this number 2. Number 2 would be when, and this one doesn't happen as often with us, but when that partial derivative with respect to x is undefined, or, now the word or comes into play, that partial derivative with respect to y is undefined. So anytime these things are undefined, that could be a critical number. Of course, it's got to be defined in the original function. So this undefined versions of these critical numbers are kind of funny. You know, they're sharp points, they're weird, they're kind of weird points. We mostly are looking at these guys, mostly.
So if they're both undefined, it's still circled.
But if it's undefined in the original function, then it's not really a critical. I mean, it's right.
Not even.
So, and that happens a lot. Okay. But this is kind of funny. So to practice finding critical points is a little trickier than you think. I mean, it's just that. It's just setting those equal to 0. And a lot of them in the book aren't too tricky, but some of them are kind of tricky. Let me see if I can find a good one. All right, so okay, so I'm in 13.8. I'm grabbing this out of the book. This is 34. 34 is a function. And it is a function of a couple variables. It is x cubed plus y cubed minus 6x squared plus 9y squared. X cubed plus y cubed. This is minus 6x squared plus 9y squared. This might not be as interesting as I thought. Plus 12x plus 27y plus 19 plus 12x plus 27y plus 19. Wow. Yeah, that's my function. All right, I'm looking for critical points. I'm looking for critical points. They're good critical points. Why am I looking for critical points? Because they're good candidates to be mins and maxes or saddle points. But anyway, I'm looking for critical points, which means basically I'm looking for this. When does the first partial derivative equal 0? When do both first partials equal 0? That's what I'm looking for. So I need fx, and I need to set it equal to 0. But I need fx and I need fy. What is fx?
3x squared minus 12x plus 12.
Huh. Okay. Yeah, this ain't as interesting as I thought. And then, I mean, I like it when the x's and y's are kind of mixed together. It looks like fx is just going to be x's. What's fy?
Just y's.
Just a bunch of y's.
3y squared.
Plus 18y's plus 37.
All right. So now remember though, I'm looking for when they both equal 0. So I'm going to set this one equal to 0, and the word "and" I think is kind of important, and this equals 0. All right, you know, with that top one, I'm moving this way. With that top one, I could divide by 3, and I get x squared minus 4x plus 4 equals 0. I'm going to proceed here. That's an x minus 2 squared equals 0. You guys okay? I divided by 3. If I did that right. And I think I just factored it. I'm getting this answer. That's when he equals 0. Now listen, I want to, you know, so what? So as of right now, for this fx to equal 0, can you name a point where fx equals 0? I mean, when does fx equal 0? When x is 2, and what did it say y had to be? It doesn't say. So what could y be? Anything. Thank you. So you know, it could be 2, -1. It could be 2, 3. It could be 2, 17. And it could be, right? Mm-hmm. Okay. So there's millions of things it could be. My point, I mean, this is stupid of me to do this, but I'm trying to make a point that y could be anything. There's a bunch of places where fx is 0. The only condition is x has to be 2. Y can be anything. And okay, so what about when fy is 0? Same game. I would divide by 3. And I would have this equation. And this is very similar. It factors into a nice squared binomial also. And so I'm getting one answer here. Y equals -3. And if I wanted to list all the places where fy equals 0, the truth is y has to be -3, but x could be anything. And so now, so there's millions of points listed there. There's millions of points listed there, but what I need is the one point that makes them both 0, and I think that would be the point 2, -3. That might have been a crappy explanation. I mean, it was actually kind of a good explanation, but you don't really see why did I do all that? Because in other problems, when it's a little more complex, you kind of gotta think like this a little bit. In this problem, x was 2, y was -3. Just throw them together, and that's your answer. But in other problems, this game of finding critical points, it's not that hard. When do these things equal 0? But it's this and, it's all the points where both of these equal 0 that you gotta, it's a little tricky sometimes. You gotta try some. I don't know if do you remember in Cal 1 when you found a critical number? Do you remember what you would do then? I mean, in Cal 1 you would find a critical number. Well, so when you found a critical number, right, it was a good candidate to be a min or a max, but you didn't really know if it was a min or a max until you. Well,
it was the first
before concavity,
first
just a first derivative test where you would be checking for increasing and decreasing, and then anyway. You'd have to do some kind of test, and then you could conclude that it's a min or a max. Well, that's what we need. I mean, what I got here is a critical number, but I don't know if it's a min or a max or a saddle point, but I do have this thing called the second partials test. It's a complicated test. Class is over today. Maybe I'll wait till Friday. Well, do you want to hear it? All right. It's this test. I mean, it's in the book. I told you have to memorize some stuff in chapter 13. You have to memorize a lot of things, but I do give you this. I'll just tell you what it is. It's the second partials test. It's kind of a trick. It says this. It says it's called the second partials test because you need some second derivatives. Here's what it says. I'm doing this very loosely here. What you do is, okay, hang on. To test a critical point, to test a critical point, hang on. To test a critical point, A, B. Let's say instead of X naught, Y naught, I'm calling it A, B. In order to test a critical point, A, B, you do this. You calculate this number D. This is a number D. Here's what it is. It's fxx evaluated at AB. You know what that is. That's the second derivative with respect to x. Multiplied by fyy calculated at AB minus fxy. That's that mixed partial evaluated at AB. That guy squared. You calculate this number D, and then here's the results. If D is greater than 0, and that fxx that you were working on at AB is also greater than 0, then that point AB is a relative min. I mean, so now I'm just shouting rules out at you here. I'm not proving this to you. In fact, the proof of this says, the proof of this has been, we're going to wait to a course in advanced calculus to prove this to you, is what the book says. So I'm just shouting it out to you, and you can read it as good as I can, but I'm helping you here. If D is greater than 0, watch this, but the fxx, see, so you're worried about calculating this number D, but then also in the process, apparently it's important to look at this fxx number here. So you're calculating if D is greater than 0 and that fxx was greater than 0, then it's a min. If D is greater than 0 and the fxx was less than 0, then it's a max. My writing might be low. There's a couple more. If D is less than 0, so if D is greater than 0, you got those options to pursue. But if D is less than 0, you don't have to worry about anything else. It's a saddle point. That point is a saddle point. And 4 is kind of funny. 4 says if D equals 0, we know nothing. The test, this test is inconclusive. This test is inconclusive. So I hope that won't happen. I give you this. You got to know your Duff formula and your gradient formula and your total differential formula. You got to know your tangent plane formula. You got to know some formulas in this chapter. But I give you this on the day of the test. Hey, we're into overtime just a tad. What? Let's just try something before we leave. What was my critical point from that last problem? Now that last problem got totally erased, but it was 2, -3. Now, in order to do this test to see what he was, I would have to do. I need fxx, I need fyy, and I need fxy. Now again, I erased those, but maybe you got them there. What would be the second derivative with respect to x? Do you?
It's 6x minus 12.
6x minus 12?
Mm-hmm.
That was before I simplified it. That was it? Good. What would be that second derivative with respect to y?
6y plus 18.
6y plus 18. And what would be the fxy?
0.
Oh, fxy would be 0, wouldn't it?
Yeah.
Because it was the derivative, it was the fx derivative taken with respect to y. And the fx was just full of x's. I remember it was full of x's. When you take that derivative with respect to y, you get a 0. All right, so I'm going to try to calculate this d. So at this point, 2, -3, here I go. I'm going to calculate this d. What I'm going to do is I'm going to stick that point into these places. 2, -3 stuck into this fxx. Well, that means that's a 12. Oh, that's a 0. And for the -3 stuck into this, I think that's a 0. And then I'm subtracting 0 squared. Anyway, so I guess what I get? D is 0, which means what?
Inconclusive.
Well, it doesn't happen too often, but it happened that time. Yeah, sorry. All right, we'll get back to work on this Friday a little bit. We can work a little Friday, and then we'll take a quiz. I don't know, maybe you guys will come in with some questions. I don't have much of an agenda for Friday. Answer your questions and do a quiz.